Okay, today we will going to develop the plane stress and plane strain stiffness equation. As we for today we will limit to the type of constant strain triangle. That's we have to starting with the theory of elasticity that we have learned. We know that the 6 components of state of stress, 6 component of stress, 6 component of stress. Six component of stress is related to the 6 component of strain by this equation. Okay, for the case of the space, the body subject force in space, and we consider the three-dimensional. Okay, for elastic, linear elastic body, that is obey Hooke's law. The 6 component of stress and 6 component of strain relate to each other by using this equation. Okay, but now if we simplify the problem into plane problem that we will talking about today, okay, we can simplify that equation in just only three equation. That is the state of the stress and strain is related to each other by just only 3 equation, and we will do how is simplified to be that. Okay, so for two-dimensional problem, two-dimensional planar element that may be defined by 3 or more nodes. Okay, it just should compose of 3 or more nodes. If we have just only 2 nodes, it's become the line element. So then the two-dimensional problem is composed of at least 3 nodes to be the rectangle shape. Okay, and if we adding a node inside of the element such as like this, maybe the increase the degree of polynomial to the displacement function. It means that we increase the number of degree of freedom also. That is normally in finite element software is composed of these 2 types. This may be the linear type. It is a non-linear type. Okay, it's a non-linear element, but it's not mean that it is non-linear problem. Okay, it is just non-linear. The degree of the polynomial is increased. Okay, and same in the same manner for the quadrilateral shape. There's if for the case of the general one, we may apply just only 3 nodes. Okay, but for some case, we may adding the node. Okay, that means that we increase the degree of polynomial to approximate the displacement function, to approximate the displacement inside of the element. Okay, and you have to note that this type of element is the area. This is the plane. So it means that we consider the value inside of this type of element. Okay, so if we compare with the line element that we have studied, as for example for bar or something, bar element or beam element, we have 2 nodes, node I and node j, right? And when we would like to find at another point, we have just only one dimension that is in x. It means that we would like to interpolate the value of this segment at this point. That is along the line of the element. But if we consider the two-dimensional problem, it means that it may be how to stay at here. This may be point P something. When we set up the coordinates, maybe set up at this point, x, y. Okay, as actually it's maybe the general one is maybe at here also. So then you will have the coordinate x, y inside here. Okay. So then what does it mean? It means that when we would like to interpolate to find the displacement in this side, we require the shape function and have to substitute the coordinate x, y into the shape function and multiply with the nodal displacement in order to approximate the displacement at this point. You see that the displacement occur or the stress occur for this type of element is mean that it is along this shaded area. Okay, it's not along the side, not only along the side of the element. Okay, it's not like the line element. Okay, this is something that is maybe different. That's I think you may understand that. Okay. Okay, then to this course, we will focus just only on the constant strain triangle, constant strain triangular element. That is the basic one for two-dimensional problem. Okay, and before we go that, we would like to simplify 3D, okay, to be 2D problem. Okay, that is actually when we derive the real problem, actually normally it should be in three-dimensional. But when we solve three-dimensional problem, in some case it may be not necessary to do like that, because the out-plane motion has the small effect on our problem. So then we can simplify the three-dimensional problem to be just only two-dimensional, because the out-plane effect is small enough to be that is not necessary to consider. Okay, in order to reduce the problem to be the two-dimensional, we have two types of that problem. First, this is the plane stress problem, and the second is the plane strain problem. Okay, first of all, we have to understand that plane stress problem and plane strain problem actually it is come from the three-dimensional problem, but we just simplify it. Okay, reduce the effect of the out plane to be the particular one that is in the plane problem. So then from that process, it may be defined two types of problem, that is a plane stress and plane strain. We have to understand this. Okay, that is the what difference between plane stress problem and plane strain problem. For plane stress problem, the definition is what? For plane stress problem, it means that we consider just only three components of stress. This means that we have sigma x, sigma y, and also tau xy. Okay. For this type of problem, it means that we have sigma x, sigma y, tau xy. For the out plane stress, it may be small enough in order and can be neglected. Okay. The out plane stress means that sigma c tau xc and tau yc become 0. Okay. Actually, it may be small. It may be not equal exactly 0, but it may be small enough in order to neglect, and we can neglect the effect of our plane stress. Okay, so then we define that this type of problem that we consider just only three stress component, sigma x, sigma y, and tau xy. Okay, is we call plane stress. But you have to note that we have three components of stress, but we have four components of strain. Because the effect of Poisson ratio. So then for plane stress problem, we have sigma x, sigma y, and tau xy. and then it related to 4 components of strain, that is epsilon x, epsilon y, and also gamma xy. And we also have epsilon c also, according to the Poisson effect. We have epsilon c. Okay, the strain, axial strain in our plane direction is not equal to 0 for this case. Okay, just only our plane stress equal to 0, but our plane strain is not equal to 0. Our plane axial strain is not equal to 0. Okay, this type of problem is what? If we consider the plate, the thin plate, that's we may like the plate subject to the strain. Okay, we may focus on this. Maybe consider we have the plate. When we would like to test the strength of the plate, okay, we apply this plate to the universal testing machine, right? And we clamp this, we apply force. Okay, the plate has the small thickness, maybe the thickness of T. Okay, and we apply the force here. So then we have the straight occur in this direction, that is in axial direction. So we may call that this is the x direction. Okay, and then the straight along y direction we will not apply. Okay, so then the y direction we may not have the straight for this case also. But for some type of problem that's we apply the load on y direction also, we have 2-dimensional direction, we may apply the load to y direction. Okay, that is the type of the case of the plane problem. We may apply sigma y also for this case, sigma x, sigma y. And for the out plane, that is because it is a thin plane, right? Okay, we may not consider the out plane straight for this case. Okay, so then what does it mean? It means that for this case, the sigma c becomes 0. Okay, sigma c becomes 0. And also for this case, we may consider just only the shear force along this, how xy, along the xy plane, just only xy. But for xc and yc, we will not consider on that. So that is a type of the plane straight that we may actually may be familiar with, the plane straight. For the case of the beam, that is one type of the plane straight. You consider like this: when beam, actually it is a 3-dimensional, right? Okay, but when we simplify beam subject to distributed load, okay, we model something like this. Okay, this is y, this is x. Okay, when it's subject to distributed load, when we consider according to the mechanics of material that we have learned, okay, when it's subject to this, okay, so what is that? We have the bending moment diagram like this, okay, and we have the shear force diagram. It's maybe like this, okay. If we consider over here, the element over here, okay, as we have the moment over here, and we have the shear force over here. So what is the state of stress of this? Okay, the state of stress of this element on the beam. This is a plane problem, right? We can simplify to be plane problem. That is what? For the axial stress, we have axial stress. Okay, sigma x equal to what? Equal to mc over I, right? Okay, and then we also have the shear force. Okay, that is tau xy. Tau xy is equal to what? Is equal to VQ over IV, right? Okay, so then this is the state of strain of this. Oh, sorry. This is state of strain of this element along the beam. Okay, and we will see that for this case. Okay, for this case, it means that sigma x, sigma y is become 0, right? For this case, okay, and the outplane also, the outplane that is the axis perpendicular to this plane, sigma c, is become 0. We not consider the strain on that. Okay, so then this type of problem, we may define this type of problem to be the plane strain. This is the plane stress problem. Are you all right for this? Okay, for another one that is the plane strain for the case of plane strain problem. For the plane strain, the definition is like this. For plane strain problem, plane strain is composed of 4 strain components. What does it mean? It means that we focus on the problem that the out of plane strain is small enough and we can neglect the effect of our plane strain. Okay, so then we have just only epsilon x, epsilon y, and gamma xy. Okay, so it means that epsilon c, gamma xc, and also gamma yc becomes 0. Okay, it's small enough and we can neglect it. Okay, but for this case, according to the Poisson effect, okay, so we have 3 components of strain. We consider 3 components of strain, but we have 4 components of stress. That is, we have sigma x, sigma y, and tau xy. And also, according to the Poisson effect, we also have sigma c also. For this case, we have 4 components. So then from definition, if we talking about the plane stress, it means that we have 3 components of stress, but we have 4 components of strain. If we talking about the plane strain problem, it means that we have 3 components of strain and 4 components of stress. Okay, this is very important to set up the problem correctly for the case that we would like to simplify the 3-dimensional problem to be just only plane. Okay, every finite element software also asks the user to define it is the plane stress or plane strain, because the constitutive relation, stress strain relation is maybe not related to each other with the same equation. A little bit different because it's come from 3-dimensional case, right? And then it's simplified to be just only 2-dimensional based on the assumption that is a different assumption. For plane stress, the assumption is that we have 3 components of stress and 4 components of strain. But for plane strain, it's based on the assumption that we have 3 components of strain and 4 components of stress. Okay, so then this is lead to the different equation to define the type of element. For the case of plane strain, what type of problem for the case of plane strain? Okay, you may consider the case of the culvert or the dam the dam is maybe easier to understand. So for the dam, type of the dam, you have the long dam. Okay, dam is very long. Okay, so then what does it mean? It means that this is if we set up this x, this y, and this c. Okay, so the dam is very long. Okay, for the type of the case that is really long, the tunnel or the something that is subject to the stress, along this body and the axial strain epsilon c along this line, okay, along the c direction. Okay, you see that because the body is very long. Okay, so then the axial strain, the deformation along the c axis, it is very small in comparison with the original length. So then what does it mean? It means that epsilon c is very close to 0. So then we can neglect it. Okay, we can consider just only in plane strain. That is mean that we consider just only epsilon x, epsilon y, and gamma xy should be enough. And epsilon c is the outplane effect that is maybe small enough. That's not necessary to consider to that. Okay, that's for the case of the very long body. That is we will apply the plane strain problem to that. Okay, so then now we know two types of plane stress and plane strain already. Okay, that is in finite element method. Okay, and in theory of elasticity, when we would like to solve the problem, the plane problem, okay, the mechanic plane problem, we have to define, is this a plane stress or plane strain? Okay, so it's very important to that. So when we simplify the three-dimensional problem to be the two-dimensional problem, okay, the 6 component of stress and strain is reduced to be just only 3 component of stress and strain. Okay, just only 3 component of stress and strain. And then we related the stress component, okay, that is composed of just only 3 components, sigma x, sigma y, and tau xy, with the 3 component of strain, that is epsilon x, epsilon y, and gamma xy, to the sum equation. Okay, and after we solve this is the equilibrium equation in two-dimensional problem, as we consider the state of stress just only in plane. Okay, and then we can find the maximum and the minimum value of the stress by this equation that we familiar with. This is an equation to find the principal stress. That is a normal stress along the plane that has no shear stress. Okay, so then if we rotate the plane to be the direction that we have just really normal stress over here. Okay, so that means that sigma 1 and sigma 2 is become the principal stress. Okay, and it's normally it is the maximum and minimum of the normal stress. Okay, of that state of stress. Okay, so for the strain, okay, the axial strain, I think you familiar with that. But for the shear strain, as we mentioned before, shear strain is defined by the change in angle. The change in angle, that is the starting angle is maybe 90 degrees like this. Okay, okay, so then the final angle is maybe this angle, that is maybe theta. Okay, so the change in angle is the gamma xy, that is equal to this is equal to the change in angle, that is if we consider this the 90 degrees become pi over 2, right, minus theta. Okay, the gamma xy is defined by the change in angle like this. Okay, that is equal to this term. Okay, partial v by partial x plus partial v by partial y. That is it's composed of these two angles. That is maybe alpha 1, alpha 2. Okay, plus to each other. This become the change in angle of the shape of the deformed shape that change from the dashed line that is in the 90 degree shape to be the solid line like this. Okay, this is the definition of the shear strain. And then we related the strain with the displacement by this equation for the small displacement case. For small displacement, this equation is limited to the small displacement only. Okay, for the small displacement. For small displacement, and then this is the small strain condition. Okay, and we have the strain, 3 component of strain. Okay, now we will consider the stress-strain relation. The stress-strain relation that is we reduce from the three-dimensional case to be the plane problem. Okay, that we have to understand that is separately defined for plane stress and plane strain. Okay, if we consider the plane stress first, for the plane stress condition, okay, we assume that the out of plane stress is small enough and can be neglected. So then we assume that sigma x, tau xy, and tau xc and tau yc become 0. Okay, we focus just only sigma x, sigma y, and tau xy. Okay, for the out of plane stress, it becomes 0, but epsilon c is not equal to 0. Okay, from this condition, we come back to the equation of the three-dimensional case, theory of elasticity, this equation. If we come back to this equation is for the general one, that is for the case of we consider three-dimensional case. Okay, so for this case, if we simplify this, equation by following this, by the following definition, that is what? That is we define that sigma c tau xc and tau yc become 0. Okay, and we know that the strain epsilon c is not equal to 0, but gamma xc, gamma yc becomes 0, right? Okay, so then what happened to this equation when we simplify with this condition? Okay, we may starting with the easy one, the easy term, that is maybe consider this. Okay, because this is the case that we consider the strain, the stress and strain, right? Okay, if we consider this term, sorry. Okay, this is the 0 case. Okay, this is a 0 case. So then when we multiply with this term, it becomes 0. That's all right. Okay. If we consider the case of gamma xy, okay, and tau xy. Okay, for gamma xy and tau xy, is what? It become E multiplied with 1 plus nu, 1 minus 2 nu. Okay, multiply with gamma xy, right? Okay, multiply with 1 minus 2 nu over 2. Okay, this term. Okay, so then for this case, tau xy, for the case of plane stress problem, for the plane stress problem, we have the relationship of stress and strain. For the shear stress, it's become what? It's become E. Okay, 1 plus nu. Okay, to rate and gamma xy. It's become like this. This is a general one. Okay. We have one term that we simplify from the three-dimensional case that actually is exactly the same as the three-dimensional case. But for the for this case, that we simplify that epsilon c, sigma c becomes 0, right? But epsilon c is not equal to 0. It is not equal to 0. So then, if we consider the third equation, what's happened to the third equation? Okay, to compare this, the third equation is become, okay, this equation sigma c is become 0, right? Sigma c becomes 0, and it's equal to what? It's equal to E multiplied with 1 plus nu. Okay, 1 minus 2 nu. Okay, and multiply with the term of, this should be symmetry case. This is a new, this new, it's new also, right? Okay, so then it's equal to what? It's equal to epsilon x mu, right? Okay, plus epsilon y mu. Okay, and plus 1 minus nu epsilon c, right? It's just for this condition. Okay, this condition, another term is become 0. And for the plane stress problem, we define that sigma c is small enough. We set up it to be 0, right? Okay, so according to this condition, what does it mean? It means that this term should be 0. That is epsilon x nu. Okay, plus epsilon y nu. Okay, plus 1 minus nu epsilon c becomes 0, right? So according to this equation, we can find that, okay, epsilon c, that is the our plane strain, actually is depend on the axial strain epsilon x and epsilon y. Okay, by this is equal to minus, okay, nu over 1 minus nu epsilon x plus epsilon y. You're right. Okay, so then we have this condition. For plane stress problem, we have this condition, that is epsilon c is equal to minus nu over 1 minus nu epsilon x plus epsilon y. From this condition, we substitute this condition back to sigma x and sigma y. Okay, so then I will show you just only sigma x. So then when we substitute to sigma x condition with the three-dimensional case, so what happened to that is become E divided by 1 plus nu, right? And 1 minus 2 nu. Okay, so this is what? 1 minus nu. 1 minus nu epsilon x, right? Plus nu epsilon y. And also we have nu epsilon c. That is, in this case, it is not equal to 0 for this case. Okay, but epsilon c is equal to what? Now we can change, we substitute this term to this. Epsilon c is become minus nu over 1 minus nu. Okay, epsilon x plus epsilon y. Okay, So then if we consider just only the term inside the bracket, so it's become what? It's become 1 minus nu epsilon x plus nu epsilon y plus what? Plus nu epsilon c is become minus nu divided by 1 minus nu. Okay, epsilon x plus epsilon y. Okay, so then this term is become, okay, e. We rearrange this term and we rearrange to be this, okay, 1 plus nu, okay, 1 minus 2 nu and 1 minus nu over here. Okay, and then this should be 1 minus nu square epsilon x plus 1 minus nu epsilon y. Okay, and this term is become minus nu square epsilon x plus epsilon y. So then what's happened? 1 plus nu and 1 minus nu is become 1 minus nu square, right? Okay, 1 minus 2 nu. Okay, this is e. Okay, so for this term, if we decompose this term, is become 1 minus 2 nu plus nu square epsilon x, okay, plus 1 minus nu square epsilon y, okay, minus nu square epsilon x minus nu square epsilon y. Okay, after that, we rearrange this term again. Okay, so this term, okay, is become 1 minus 2 nu epsilon x, okay, okay, and plus nu square epsilon x, okay, is plus, okay, 1, this should be epsilon y minus nu square epsilon y, okay, this is minus nu square epsilon x minus nu square epsilon y, right? Okay, what's happened? This term is cancelled out. Okay, and then we have for this term 1 minus 2 nu epsilon x. Okay, for this case, we see that what happened? This should be 2 nu square epsilon y, right? Okay, so then what does it mean? It means that is equal to 1 minus, this should be nu. I'm sorry to that. I've got nu over here. It should be nu. Okay. So then it's become nu. Okay. 1 minus 2 nu. Okay, epsilon y. Okay. So according to this, is become e over 1 minus nu square, right? Okay, multiply with epsilon x plus nu epsilon y. You all right? We have this equation. For the same manner with the sigma y, also we simplify with the same procedure. Okay, we obtain. So then for this case, we obtain the plane stress equation, that is we simplify already to be like this. Okay, I have to move here. Okay, so then the plane stress equation, that is sigma, is become sigma x sigma y and tau xy. This is related to D, that is become metric D, that is defined by this. Okay, multiply with epsilon x, epsilon y, and gamma xy. Okay, over here. Okay, gamma xy. As the for this case, you see that sigma x actually is equal to from the previous equation that we derived. We have sigma x is equal to what? Is equal to E. Okay, over 1 minus mu square. Okay, and epsilon x plus mu epsilon y. If you compare with the above derivation, okay, but for tau xy, actually from the previous one, we found that tau xy actually is equal to E, okay, over 1 plus mu, okay, and 1 minus 2 mu, okay, multiply with what? Multiply with 1 minus 2 mu, okay, over 2 epsilon, gamma xy. So you see that this term is cancelled out, okay, but in order to rearrange the equation to be this term, okay, so then what's happened? It means that it is equal to, this term is equal to E, okay, multiply with 1 plus mu, okay, 1 minus mu, right, and 1 minus mu above, okay, gamma xy and 2. Okay, so then this term is 1 minus mu square. Okay, then that is the plane stress equation is become this. Okay, don't forget, it's very important to select the condition. If you simplify your problem to be plane stress, you have to use the constitutive element. That's the constitutive equation. That is a constitutive metric D. It has to select the correct metric D also. This for the plane stress condition. For plane strain condition, you will see that it's very close to the three-dimensional case because it's simplified directly by the strain. Okay, for plane strain condition, what does it mean? It means that you have 3 components of strain. That is, you have epsilon c, epsilon x, epsilon y, and gamma xy. And you simplify that. The strain, the outplane strain is small enough and can be neglected. So then we can set up it to be 0. For that case, what does it mean? If we come back to the three-dimensional case, you will see that we just simplify that epsilon c, gamma xy, and gamma xc become 0. So then we reduce it directly. Okay, we reduce it directly for the right hand side. That is epsilon c, gamma yc, and gamma xc become 0. Okay, and we can find the sigma x, sigma y, and sigma c directly. That is not necessary to rearrange the equation from three-dimensional, and you will see that the term is very close to the term of three-dimensional case that we just eliminate the term of our plane strain. Okay, that is the case of plane strain. And you have to note that for the plane strain condition, the metric D, okay, comparison with the metric D for plane stress is different. Okay, it's up to the problem that we define. That is very important to define. Okay, so then I will stop this clip over here and let you ask some question.